really important that everybody be super duper comfortable with these three things. The matrix A is not invertible. Means the same thing as the matrix A being singular, which means the same thing as the determinant of that matrix A equaling 0. So all these things mean the same thing. And someone's going to assume that if you say one of them, that you know the other one is also true. So if I say matrix not invertible, I'm like, oh, the determinant is 0. And then the other things are true as well, right? If all these opposite things are also equivalent. The matrix is invertible if and only if it's non-singular, if and only if the determinant is not 0. And again, the way I would encourage you to kind of remember this, which I think Burke did a good job of talking about last on Monday in class, is that, right, a matrix is invertible, just like any real number is invertible except for 0. Sorry, so when it's not invertible, its determinant is 0, which is also a not invertible number, right? We can't find the inverse of 0. But A is invertible if its determinant is something like 5, because 5 is an invertible number. So there's a nice connection to be made there as well. Let's look at some examples though. So let's talk about how to find, or let's actually not talk about it, because I think she talked very well in class about how to find eigenvalues and eigenvectors of a matrix. Let's just do a bunch of examples and then we'll do some other stuff. So let's say we've got this matrix. A is the matrix 3, 6, -1, -4. Now I want to find the eigenvalues and eigenvectors. And almost always, if you're being asked to find the eigenvalues and eigenvectors, you kind of have to find the eigenvalues first. She's definitely right in this class. We typically only see matrices that have distinct eigenvalues. So we can usually count on a 2x2 matrix having 2 different eigenvalues, but it's certainly possible in general for a 2x2 matrix to have 1 repeated eigenvalue. So what we usually say is an n by n matrix has as many as n distinct eigenvalues, but it can have less. But in this class, it's almost always whatever size your matrix is. Okay, so then we're going to find them. Is we're going to solve this equation. We're going to solve, this is called the characteristic equation, by the way, the determinant of A minus lambda I equal to 0. I'm happy to get into why this is what we're doing if you guys want, but that's what we're doing. So A minus lambda I is just our matrix minus lambda times the identity matrix. Usually what we do is we get into the habit of just sort of saying, okay, we're just going to subtract lambdas from the diagonals. This is going to be 3 minus lambda, 6 minus 0, -1 minus 0, and -4 minus lambda. Okay, so that's our A minus lambda I. Now we're going to find the determinant of that. So the determinant of A minus lambda I is equal to, let's see, we know how to find determinants. It's the product of the diagonals minus the product of the off diagonals. So it's going to be 3 minus lambda times -4 minus lambda minus 6 times -4. And now we're going to simplify this. This is almost always, at least for a 2x2 matrix, going to result in a quadratic equation. Most of the time, a lot of the time, it's going to factor. Let's multiply this out. So let's see, I'm going to get, oh, and we're going to set this equal to 0. Sorry. So we're going to get, let's see here, 3 times -4, 3 times negative lambda, negative lambda times -4 is plus 4 lambda, negative lambda times negative lambda is plus lambda squared, minus 6 is plus 6 equal to 0. So it looks like I get lambda squared plus lambda minus 12 plus 6 is -6 equal to 0. And that does factor. That factors as lambda plus 3 times lambda minus 2 equal to 0. So we found our eigenvalues. our eigenvalues are lambda equal to -3 and lambda equal to +2. Okay, let's find the eigenvectors. So again, here's our matrix A. I forgot what it was, 3, 6, -1, 4. And we found our eigenvectors to be lambda equal to, let's deal with lambda equal to +2 first. Okay, I'll call this lambda 1. So we're going to try and solve the equation A times the eigenvector V1. That's what we're trying to find. We're trying to find the eigenvector V1, which we're going to call XY. We're trying to solve A times V1. Let me write it down here so there's a little more room. A times the eigenvector V1 is equal to, throw my pen on the floor, is equal to lambda times the eigenvector V1. But lambda is 2. So we're trying to solve this matrix, 3, 6, -1, -4, times the eigenvector that we're trying to find, xy, equal to lambda times xy. Okay, oh sorry, lambda is 2. Apologies. I would like to show you 2 different ways to do this, because although I think the calculation she's doing in class is perfectly good, it's maybe a tiny bit more work than you actually really need to do. But I'm going to show it to you her way first, and then I'll show you a slightly smoother way, I think. So what she's doing is she's saying, right, this here we're going to rewrite as 2 times the identity matrix. So right, this is going to be the same as 3, 6, -1, -4 times xy equal to 2 times the identity matrix. So 2, 0, 0, 2 times xy. I want to make sure everyone's cool with this, right? The right-hand side didn't change. 2 times the vector xy gives you 2x, 2y. This matrix times the vector xy gives you 2 times x plus 0 times y, and then 0 times x plus 2 times y. It's still going to give you 2x, 2y. So both of these right sides are the same. They're just written differently, and they're written this way, so then we can subtract this matrix minus this matrix. So we can go ahead and rewrite this as 3 minus 2, 6 minus 0, -1 minus 0, -4 minus 2, times the vector xy equal to the 0 vector. So we subtracted this over here. And then we said, oh, this matrix minus this matrix is that matrix there. So now we're left with the following. 1, 6, -1, -6, xy. 0, 0. Okay. And then you actually only need, with rare exception, you only need to deal with one of the equations, meaning you only have to do like the first row dotted with the column. You don't need to deal with the second row. So if I write 1x plus 6y equal to 0, I could also write -1x minus 6y equals 0, but that's essentially the same equation. And then you can solve for y like that, and definitely, I mean, it does give you the line in class, so we probably should solve for y. So I solve for y, I get 6y equal to -x. I get y equal to -1/6 x. Okay, so I'm gonna go back to this side for a second. So here's the line. Y equal to -1/6 x. There's lots of points on this line. There's the point 0, 0. There's the point, well, I mean, there's the point 1, -1/6, 2, -2/6. But the point I'm going to pick that's easy to see is the point 6 comma negative 1. And that point is what I'm going to choose to be the terminal point of my eigenvector. So I'm going to say that for this equation, I'm going to pick my eigenvector. It's going to be 6 negative 1. And really what I'm actually kind of doing is I'm taking a page from her book. I'm saying, hey, look, right here, I've got 6y equal to negative x, or if you prefer, 6y equal to negative 1 times x. Let x be 6 and y be negative 1. Essentially picking the coefficient of y to equal x and the coefficient of x to equal y. So that 6 times negative 1 equals negative 1 times 6. Oh, x is 6, y is negative 1. There's my eigenvector. Okay, so, and like she was saying in class, right, clearly there are an infinite number of options, right? We could have picked x equal to 12 and y equal to negative 2, or x equal to 60 and y equal to negative 10, or x equal to negative 600 and y equal to 1, right? There's an infinite number of possibilities. The only thing you're not allowed to pick that's a multiple of this vector is 0, 0. The 0 vector is not allowed to be an eigenvector. So there's one of the eigenvectors on this eigenline. It's often this thing here, this is called an eigenline. It's the line that all the eigenvectors would land on if they started at the origin. And yeah, you can pick any point on there that you want, but usually either picking 6, negative 1 or negative 6, positive 1. Those are the typical choices for what the eigenvector is for this eigenvalue of lambda equal to 2. Okay, let me say one thing. I feel like this is kind of a lot of work. I would like to show you a slightly easier way. So the slightly easier way, so again, you should be aware of both things because I feel like she is showing it to you this way. She might expect you to know it that way. But you don't have to actually do any work with this. You can say, well, look, I can still solve this equation, right? If I do 3 times x plus 6 times y equal to 2 times x, if I subtract 3x, look, I get the same thing I got over there. I get 6y equal to negative x. That's exactly going to give me x equal to 6 and y equal to negative 1. Sorry, I said positive. It doesn't really matter, but trying to be consistent. I feel like that's way easier than having to write the identity matrix and your eigenvalue and then bringing everything to the left. And then, I mean, it's not like a ton easier, but it is a bit easier. So we can do it either way. I will probably continue to show you both ways, but that's our eigenvector for this eigenvalue. So far, for this matrix, we have the eigenvalue of lambda 1 equal to 2, and the eigenvector of 6, negative 1. And I guess I'll erase on the other side to clean this up. Because we still have the other eigenvalue of lambda equal to negative 3. I'm going to say this stuff at the top one more time, and then I'm going to erase it. Not invertible is the same thing as being singular, is the same thing as the determinant being 0. And then invertible is the same as non-singular, is the same as the determinant of a matrix is not 0. So make sure that those are crystal clear in your brain. So for lambda equal to negative 3. So again, we're trying to solve, I guess I should call it lambda 2, right? It's my second eigenvalue. And my second eigenvector, again, I'm still going to use the letters x and y. So we're trying to solve the equation A times our eigenvector equals our eigenvalue times our eigenvector. Okay. So one way you can do this is you can do what we did over there and say, okay, well, this is really, so I'm gonna do I'm gonna subtract and do this at the same time. So I'm gonna say I've got this. I have 3, 6, -1, -4 times x, y. Minus a -3 is gonna be a +3, so it's gonna be +3 times the identity matrix, 1, 0, 0, 1 times xy equals 0, 0. And I subtracted this over and I tossed in the identity matrix. We're always allowed to multiply a matrix by the identity matrix. It's like multiplying by 1. So then I've got this, and then I'm just gonna do 3 plus 3, 6 plus 0, -1 plus 0, -4 plus 3. The shortcut you can always take instead of writing all this out is essentially you can just take your matrix, your A matrix, and you can say, oh, I'm just going to do A, and then in the diagonals, I'm subtracting the eigenvalue. Right? This matrix here is just A minus lambda I. You're taking your matrix A, and in the diagonals, I'm subtracting -3. Oh, 3 minus -3 is 6. -4 minus -3 is -4 plus 1, which is -1. And then we write out the equations. 6 times x plus 6 times y equals 0. So 6y equals -6x, or preferably y equals -x. So in this case, I would pick x equal to 1 and y equal to -1. So my eigenvector would be 1, -1. Or we can do it over here. If I just start off right away by saying I'm going to multiply this or dot this with this equal to that, 3x plus 6y equals -3x. Solve for y, 6y equals -6x, y equals -x. You get the same thing. There's the line y equal to -x, and literally pick any non-origin point on the line, like 1, 1, or -2, 2. And the vector that goes to that point is your eigenvector, or the vector that goes to this one. Any vector on the line is an eigenvector. So the eigenvector we could say is 1, -1. You could just as easily say that the eigenvector is -300, 300. That would also technically be correct. Usually we default to picking kind of the eigenvector that has the smallest integer values. So like we try not to get fractions in there if we can help it. Like in this previous example, right? If you'd wanted to, you could have picked the eigenvector where x was 1 and y was -1/6. But we usually try to make choices that result in integer entries for each of the components of the vector. Okay, before we do more examples, are there any questions about this example?
I was just wondering if your way is like, to me your way is like so simple, but like why are we doing it the other way if there's such a simple way to do it?
I mean, they're really the same. I will point out they are literally the same, right? I mean, we're getting to the same equation, right? It's just that I'm doing the multiplication first, but I mean, right? We're doing the same work. In fact, let me show a little bit more work here just to really emphasize how the same they are. I'll leave this over here. All right, all I'm really doing is instead. So what I'm doing, right? I'm starting with this. Actually, I can say a little more. Right, and I suppose I could rewrite this like that, right? Where I say, oh, really, this is 2 times the identity matrix times xy. So we did it that way, which yes is the longer way. We do it this way, it's the same work, right? And so what I'm really getting here is 3x plus 6y. That's the first entry of this side of the product. And then I'm getting negative x minus 4y. On the right side, I'm getting, let's see, so 2x and 2y. Really, that's the same thing I'm getting here, right? So here I'm getting 3x plus 6y equals 2x, and negative x minus 4y equals 2y. Here I am getting the same thing. Look, I'm getting 3x minus 2x plus 6y. That's the same as this. It's just yeah. Right here, I'm getting 3 minus 2x plus 6y. That's the top row. And here, if I do the multiplication, I'm getting negative x plus negative 4 minus 2 times y. But if you look at these equations, they are the same. This equation says 3x plus 6y equals 2x. If you subtract the 2x over, it's 3x minus 2x plus 6y equals 0. That's exactly the same equation I have here. 3x minus 2x plus 6y equals 0. Same deal down here. This is, oh, sorry, I forgot the x there. Apologies. This is negative x minus 4y equals 2y, or negative x minus 4y minus 2y equals 0. This is negative x minus 4y minus 2y equals 0. So I really, and I don't think you missed this. I just wanted to say it many times. Both ways of doing it are the same. The reason you might do it this way is because, okay, there is it's not really a good reason. It's a kind of mathematical reason. Also, it's hailing at my house, by the way. It's kind of neat. Not that I've never seen hail before, but you know, we don't get hail here a whole lot, so it feels kind of like an event when it happens. So yeah, it's hailing outside. There was some lightning and thunder earlier. But the reason that, so here's the difference, basically. The difference between what I did and what she did is I solved this, a times v equals lambda v, right? And I have my a11, a12, a21, a22. My v is my xy and my lambda. Right? I solved that, whereas she correctly, and I think very appropriately, solved this. A minus lambda I times v equals to 0. And doing it this way, so literally, I'm going to say this a few times, a minus, oh, I should write lambda I now. I mean, it doesn't really matter, but we usually write the coefficient lambda in front of the matrix I. A minus lambda I is just the, right, or I should say, right, lambda I is just that matrix there. Lambda is on the diagonals, 0 everywhere else. So A minus that matrix, you're just subtracting lambdas on the diagonals, and you're getting this. A11 minus lambda, A12, A21, A22 minus lambda, times xy, 0, 0. I guess I'm kind of going in circles a little bit. I'm just trying to say they're the same. But the reason, I guess, you might do it this way is because people do talk about how the eigenvectors, the eigenvectors, are in the null space of this matrix. I know we haven't talked about the null space. That's not something we usually talk about in this class. The null space of a matrix is the set of all vectors that if you multiply your matrix by that vector, you get the 0 vector. So that's one reason people, and it's called the eigenspace of a vector when you talk about the null space of this particular thing. So that's why someone might prefer to think of it this way, because it has some kind of more typical mathematical setting. But as far as the math is concerned, and I should really say, I should back up a little bit. For 2 by 2 matrices, this works great. For larger matrices, this does not work so great. The thing is here, for a 2 by 2 matrix, when you're solving this kind of thing, I still get loud out there. Or when you're solving this kind of thing this way, you kind of have very limited options, right? You only have 2 variables you're dealing with. So once you say, oh, well, I know that this is equal to this, you can always write one variable in terms of the other, right? This totally leads me to 6y equals negative x. So great, we're done. When you have larger matrices, you have more variables. And so you can't just say, oh, y is this in terms of x. It becomes much harder. So that's another reason that's actually a much better reason that I finally came up with to do it the way she's talking about, where you actually are saying you have a matrix, because a matrix times your eigenvector equal to 0. And you probably won't take linear algebra, but if you did take linear algebra, you would learn about how there's lots of methodology about how to solve a matrix times a vector equal to the 0 vector. And so this is probably the more standard way of looking at it because it works for any size matrix. This is kind of a special thing we can do because we're dealing with 2 by 2 matrices. So hopefully that kind of answers a very long answer to your question, but I think that might be a good answer. That said, you're probably perfectly welcome to do it this way, but you should be aware, right, that there's this other kind of setup, and she might ask you things about doing it this way. So that's why I'm kind of showing you both. Okay. I think it might be more rain now than hail. Yeah, it's rain. It's not hail anymore. Okay. Let's see. So let's do some more examples. Yeah, let's look at this example. I will also just mention, well, let's do this example, then we'll get to the place here. So let's look at this example. A equal to, what's my matrix here? 2, 6, 1, 3. And I want to do the same sort of thing. So I'm going to find the eigenvalues, I'm going to find the eigenvectors. We always have to start with finding the eigenvalues. So we're always setting the determinant of A minus lambda I equal to 0. Okay, A minus lambda I is something you should get really comfortable writing down. Right? If that's A minus lambda I is just the same matrix with negative lambdas also on the diagonal. So we're going to get 2 minus lambda, 6, 1, 3 minus lambda. It doesn't actually matter what size your matrix is, right? If someone said, if we were going to start trying to find the eigenvalues for a 3 by 3 matrix, like if my matrix was B equal to, I don't know, 3, 0, 0, 1, 2, 4, 0, 1, 0, I was going to find the eigenvalues of this matrix. Not that we have the tools, but the setup would still be to set the determinant of B minus lambda I equal to 0. So we'd be taking the determinant of this matrix minus lambda in the diagonal. So 3 minus lambda, 0, 0, 1, 2 minus lambda, 4, 0, 1, 0 minus lambda. And then you would have to take the determinant of that. But it's always, when you're finding eigenvalues, it's always take the determinant of your matrix minus lambda times the identity matrix. So we're going to be taking the determinant of that. So that's going to be, I don't know if she's used this notation in class, but one notation for writing the determinant is, it looks like the matrix except it's an absolute value. So that's not really, it looks like a matrix except you're using vertical lines instead of brackets. So this notation here, you might see this. That's notation for the determinant of that matrix, right? They're not brackets like this. They're just straight vertical lines. That's the way people write the determinant of a matrix. So the determinant of this matrix is going to be, let's see, 2 minus lambda times 3 minus lambda minus 6 times 1. All right, so that's going to be, let's see, we should get it multiplied out. So I'm going to get a minus lambda to the minus lambda to the lambda squared. I'm going to get a minus 3 lambda minus 2 lambda. That's going to be a minus 5 lambda. And 3 plus 2 is 6. So I'm going to plus 6 and the minus 6. So those are going to cancel out. So there's my determinant right there. So that's going to be lambda times lambda minus 5. Interesting. Yeah. So let's go ahead and find the eigenvectors. So if we set lambda equal to 5, do I want more room? I want more room. Fine. Okay. So lambda equal to 5, we're going to do a times, notation. Let's go with notation. So usually we call our eigenvectors lambda 1 and lambda 2. So lambda 1 is 5 and lambda 2 will be 0. Doesn't matter which order you pick. So we're going to do, right, our matrix times our eigenvector equal to lambda times our eigenvector. And again, we are thinking of our eigenvector as the vector x, y. So let's see, I'm gonna have a 2, 6, 1, 3 times x, y equal to lambda 1, which is 5 times x, y. Okay, let me show you the short way. Use the first row dotted with the first column. 2x plus 6y equals 5x. Subtract x, 6y equals 3x. Usually I don't divide by the coefficient of y, but I think that's what she wants you to do, so you can see the line. So I'm going to have y equal to 1/2 x. So the line, the eigenline, would be the line y equal to 1/2 x. Yeah, I think I can erase this. So this line here, y equal to 1/2 x, that goes with the eigenvalue, lambda 1 equal to 5. Pick any point on it. I'm going to pick not x equal to 1, but x equal to 2. So my eigenvector is the point 2, is the vector 2, 1. Or we could have done it the other way, right? We could have said, I guess I'll do it on the other side. Okay, I do think though, here's what I will say about doing it the other way. I do think it's really okay to jump from this step, which I don't remember what it was now, 2, 6, 1, 3 times xy equal to 5xy. I think it's really okay to jump to this. 2 minus 5, 6, 1, 3 minus 5 times xy equal to 0, 0. I don't think Karan would disagree with that, but I really feel like you don't need to say, okay, this is really, 2, 6, 1. Oh wow, this pen is really done, is what it is. So you could have done as well. It's just these two guys, all right. So 2, 6, 1, 3 times xy equal to 5 times the identity matrix. And then you're subtracting this to say 2, 6, 1, 3 times xy minus 5, 0, 0, 5 times xy. I don't feel like you need to do all of this. I think you can just jump straight from here down to there. And then look, we're going to get -3, 6, 1, -2, xy. There is something I do like about this way. And the thing I like about it is when you do it this way, the matrix you get over here after you've subtracted the other matrix over, the rows of this matrix are always going to be multiples of each other. Now, in this particular example, we actually started with a matrix where that was also true, but in the previous example, we did not. So when we say that the rows are multiples of each other, what we're really saying is the equations are the same, right? If I multiply this out, negative 3x plus 6y equal to 0 is literally the same equation. It just looks a little different as 1x minus 2y equal to 0. Both of these equations represent the same line. Both of these equations have the same set of solutions. They're both going to be y equal to 1/2 x. So again, I probably would recommend doing it this way because it's so much more computationally easy. But I would also point out that you probably should be aware of this process as well. Let's go ahead and find the other eigenvector. So our other eigenvector was lambda 2 equal to 0. So we're going to now solve our matrix 2, 6, 1, 3 times our eigenvector, which we don't know, equal to the eigenvalue 0 times the eigenvector. So again, right, the eigenvector can never be the 0, 0 vector, but the eigenvalue is certainly allowed to be 0. So when we do this, let's see, we get 2x plus 6y equal to 0. Solving for y, 6y equals negative 2x, y equals negative 1/3 x. And if I had to pick, I would pick x equal to 3, y equal to negative 1. So that my eigenvector was the eigenvector 3, negative 1. Back to my picture. Y equal to negative 1/3 x looks a bit like this. And that's associated with lambda equal to 0. And like, so here's the vector, you know, we picked 2, 1. And here's the vector we picked 3, negative 1. Those are our eigenvectors. The whole point of an eigenvector is that when you multiply the matrix by the eigenvector, you get a vector that's a multiple of the eigenvector, right? So if that's an eigenvector 2, 1, then the matrix times that eigenvector is going to be 5 times that eigenvector. So it's going to look kind of silly here, but let me use my less good pen. Let's try to save the ends of pens for drawing over other things, right? So if this is my eigenvector v1, then here is a times v1. I multiplied it by 5. But it didn't change the direction. It's going to be kind of silly for v2, because if this vector is v2, then there's the vector a times v2. It's kind of the dumbest vector ever. It's the 0 vector. It doesn't have any length, but that's what you get when you have an eigenvalue of 0. Also worth noting, if your vector happens to, if your matrix happens to have 0 as one of its eigenvalues, that means that the matrix actually is singular or not invertible. If one of your eigenvalues is 0, it means that the determinant of your matrix is 0. Right? And the determinant here is 0, right? 2 times 3 is 6, 6 minus 6 is 0. So if you notice that one of your eigenvalues is 0, you can automatically conclude that your matrix is not invertible. Kind of interesting. How much time we got? Do I have time for this? Yeah, I got time. Okay, cool. Let's do one more example because this, I've got one more example where this kind of thing happens. And then I can remember something. Sure. So you might notice that in each of these examples for a 2x2 matrix, we're getting a quadratic equation. Did I erase it already? No, I didn't, right? So right here, right, we're getting some quadratic equation in lambda. And you might remember that a quadratic equation doesn't always have real solutions. all of our examples in 17b will, right? So every, or at least should, unless something crazy happens on the next last day of class. But I will warn you, in 17c, we are going to talk about matrices that have eigenvalues that are imaginary, where you have a square root of a negative. So that is something that's coming our way next quarter. Just be prepared for that. We're gonna be finding the eigenvalues of a 2 by 2 matrix, and sometimes we're going to get imaginary or complex values. Not yet though. That's for next quarter. Okay, let's look at one more example. Also, as far as reviewing for you guys' final, I think I've decided I haven't decided exactly the time, but I think I've decided I'm going to do the reviews for this class and the other class I'm doing on Monday. So that then if you aren't able to make it to the review, you'll still be able to see the video that I will upload after. And then on Tuesday, I'll have office hours. And then Wednesday, you guys will have your midterm. So I think that should work all right. I apologize to those of you that won't be able to make it to the live version if you want to make it to it, but decisions had to be made, so I made decisions. All right, so same deal here. This matrix, actually, let me point out a few matrices. This matrix, let's see, 2, 0, 6, 5, and this matrix, 9, 0, 0, 7. All these matrices are special. This is called an upper triangular matrix because everything above the main diagonal, or I should just say everything below the main diagonal is 0. Right, so this is called the main diagonal. Everything below it is 0. It's upper triangular. This matrix, I don't think you'll be surprised to learn that this matrix, where everything above the main diagonal is 0, this matrix is called lower triangular. And lastly, this matrix where everything that's not on the diagonal is 0 is called diagonal. And I don't really care about these names, but what I want you to know is that when you have a matrix that's like this, where everything either above or below or both is 0, I should say above the main diagonal, below the main diagonal, or both above and below the main diagonal, the eigenvalues are super duper easy to find. You don't have to do any work. The eigenvalues are just what's on the diagonal. Here, the eigenvalues are 3 and 4. Here, the eigenvalues are 2 and 5. Here, the eigenvalues are 9 and 7. Let's see why. Let's look at this matrix here. If I was going to do the determinant of A minus lambda I, I'm going to do the determinant, let's see, it's going to be the determinant of this matrix minus lambda is on the diagonal. So 3 minus lambda, 1, 0, 4 minus lambda. But now look, the determinant of this matrix is the product of the diagonals, 3 minus lambda times 4 minus lambda, minus the product of the off diagonals. But look, and I just said that, one of the off diagonals is 0, meaning the product has to be 0. So if you have a 0 here, or a 0 here, or both, this part here is always going to be 0. So you're just going to get this times this. But if you're just going to get something minus lambda times something minus lambda, those somethings are going to be your eigenvalues. So we've got 3 minus lambda times 4 minus lambda equal to 0. Well, lambda equals 3, lambda equals 4. So something that's worth recognizing. This will definitely save you some time. If you see that you have a 0 in this lower corner or this upper corner or both, you automatically know what the eigenvalues are, which is kind of great. All right, let's find the eigenvectors because there is something that's a little bit interesting here. Something that I feel like can take a little bit of getting used to. So let's see, our matrix was 3, 1, 0, 4. And our eigenvalues, let's say lambda 1 is 3, and let's say lambda 2 is 4. So let's do it for 3 first. So I'm going to do A, and that's a V1. Sure. So 3, 1, 0, 4 times the eigenvector xy, equals 3 times xy. Right. Okay, so let's multiply out the top row. So 3x plus 1y equals 3x. Okay, so what am I going to get? This might seem like it's not enough information, but it actually is. Sometimes I get that in mind, well, let me look at the second equation. It's not going to help either. All right, the second equation is 0x plus 4y equal to 3y. Subtract 3y, you're still going to get y equal to 0. Y equal to 0. Oh, we actually know what that line looks like. I really like so I never thought about like thinking about the lines before. Really, I really like that she has you guys do that, because if you think about the line y equal to 0, then it's easy to find a vector on it. Pick a point, any point. I'm going to pick 1. There's my eigenvector. My eigenvector is 1, 0. An eigenvector can never be 0, 0. But if you're getting one of the variables equal to 0, the other one has to be not 0. You can pick any not 0 number you want, and it'll be a vector. And any other one, right? You can pick 1, 0. I can pick 5, 0. You can pick 6, 0. Someone else could negative infinity, negative a million 0. Right? So if one of them 0, make the other one 1 is usually the choice, but you can pick really anything. All right, let's find the other eigenvector. So let's see if we have now 3, 1, 0, 4 xy equal to, what do I got here? 4xy. I do want to point out that the second equation here is actually not helpful at all. So if you do the second equation, or from the second row, as 0x plus 4y equal to 4y, that just tells you that 0 equals 0, which is true, but not helpful, right? The 4y's cancel and you get 0 equal to 0. So if you ever get that as your first equation, you do need to definitely look at the second equation. So let's look at the other equation. So 3x plus y equals 4x. Subtracting 3x, I get y equal to x. So my other vector is 1, 1. Y equals x. That went there. Oh yeah, 1, 1. So my vector here is 1, 1. Okay. I think we're out of time, so I will stop talking. But definitely so I will say, you want to make sure that you're very comfortable doing this. 1, because it's going to be on your test. And 2, because you are really, really, really going to be doing a whole heck of a lot of this in 17C, right? Finding eigenvalues, more eigenvalues than eigenvectors, although you do still find eigenvectors, but really, really like being super comfortable finding eigenvalues is a lot of what we do in 17C. So you want to get good at it. It should be something that you should be able to do very fast. So practice it. Practice it as much as you can. And I will see you guys on Friday. I will post announcements about reviews and stuff today. And then I'll see you guys on Friday and then next week. All right, before you go, let me just take a quick screenshot of who's here. Okay, now you can go. I'll see you guys later.
Thank you.
You're welcome, yeah.
Hi, Professor James. I have a quick question about
Okay, go ahead.
So you said we can use the diagonal values to find the eigenvalue. Why can we find, like, for this one, why can we have 3 as an eigenvalue?
Well, because 3. So the reason 3 is the eigenvalue is because it's the solution to this equation.
Mm-hmm.
Right. So
how about the method that you just taught us, like the diagonal, like on the top of the whiteboard?
Oh yeah. So what I'm saying, is that if we happen to have a special matrix like these, where you have a 0 here, or a 0 here, or a 0 here. You can still do it the regular way and say, oh, it's the determinant of a minus lambda I. It's this, and we solve this equation equal to 0. And we still get lambda equals 3 or lambda equals 4. But what I'm also saying is you can totally skip this, because when you have a matrix that's like that, it's always going to be the values that are on the diagonal.
Oh, okay.
But then we still have to do the work to find the eigenvector.
Yeah, so like it can be any numbers as long as it has like that format. It doesn't have to be 3 and 4, right?
Right. Well, because this one, the eigenvalues are 2 and 5.
Okay, you're just doing it based on the format because it's like it has a 0 on the top left and like or top right.
So what I'm saying though is like if you had this matrix, the eigenvectors are not, or sorry, the eigenvalues are not 1 and 4.
Mm-hmm.
You have to work for them. But if we happen to have a matrix where you have a 0 in this corner, or both corners, then there's a shortcut that says, oh, we already know the eigenvalues are just whatever's on the diagonal.
Okay. How about if there's like the 0 on the another diagonal, like top left and
sure,
bottom right?
So
Does it still work?
That's not helpful at all.
Okay, it doesn't work.
Nope, doesn't work.
Okay. I think I got it. Thank you.
Oh,